All right, we'll continue with these exercises. Again, we're finding critical numbers, we're finding the intervals on which functions are increasing or decreasing, we are finding relative max and min, and we are using the graphing calculator to check our results here. So we have been going through quadratics, cubic functions, functions to the fourth power. I'm not sure. Here we're going to have one to the fifth power. Again, I'll do the odds. You should be working on the evens on your own and double checking your results with your calculator to make sure that you got everything correct. Alright, so we go ahead, and number 25 is f of x equals 1/5 of x to the fifth minus 5x. It's much easier to do that than it is to try to do a quotient rule with just a constant in the denominator. So derivative, constant multiple rule says the constant comes out. And we'll have 5x to the fourth, then minus 5. And that's it. Now we can multiply through by 5, and we get rid of the fraction. Fortunately, in this case, maybe not in every case. So we end up with x to the fourth minus 1. We'll put that into factored form, which would be x squared plus 1 times x squared minus 1, which again can be factored to be x squared plus 1 times x plus 1 x minus 1. So that is the factored form of our derivative. If we want to highlight that, we'll use that in our first derivative test. Now, our critical numbers. X squared plus 1 is never 0. Then our critical numbers are x equals -1 and x equals 1. We make our number line with our critical numbers, and we remind ourselves that we're working with the first derivative here. Find some test points. 0 is good, 2, -2, and we're going to plug them in. Now whatever we plug into x squared plus 1 is always going to come out positive. So we only need to worry about the second and the third factors. So plugging in -2, I get negative and negative, which is positive. Plugging in 0, I get positive and negative, which is negative. Plugging in 2, I get positive, positive, which is positive. And so again, I have something that has this shape to it. And even though it's a fifth degree function, there's only 2 relative extrema. There are only 2 relative extrema in there. So we want to record then where the function is increasing. Increases from -infinity to -1, and from 1 to infinity. Decreases from -1 to +1. We have a relative max at -1, relative max at -1. We'll see what the y-coordinate for that is. And we have a relative min at +1. Okay, so let's see if we can tell. We go back to the original function for the coordinates of the relative extrema. Plugging in 1, I get 1 minus 5, which is -4, over 5, which is -4/5 for the minimum. Plugging in -1, I'm going to get -1 minus -5, which is -1 plus 5, or 4/5. And that should about do it for this. We'll just double check our results with the graphing calculator and see how we did. Alright, so we'll put our function in. We have parentheses x to the 5th power minus 5x, close parentheses, divided by 5. And we should be able to zoom standard, and we get a graph that has the shape we're looking for. Let's go in and find our relative extrema. Second, calc. We'll look for the max first. That's option 4. Left bound, -3. Right bound, 0. And we get that that is at 0.8, which is 4/5. So that's good. And we'll check the minimum, option 3. So left bound 0, right bound 3, and we got -0.8, which is all good. So I'm going to just save a copy of this, and we'll go on to the next problem. I just adjusted the window a little bit to go from -5 to +5 for x's and for y's, and that'll be a little bit clearer to see. All right, we'll go on to the next problem in a second. All right, in number 27, we have a slightly different type of function. We have this function with a rational exponent, or x to the 1/3 plus 1. So 27, f of x is x to the 1/3 plus 1. F prime of x is 1/3 x to the -2/3, and the derivative of 1 is 0. Now this is never 0, because let's write it this way. We would get 1 over 3 times x to the 2/3. A rational function is 0 when its numerator is 0, but x equals 0 is a critical number, because at x equals 0, f prime of x does not exist. And so that is our one critical number in this case, and we'll go ahead and make our sign chart. Now the original function is defined for all values of x, and at x equals 0 we're going to test to the left. We have a -1, to the right a +1, and we're working with f prime of x. So we're going to plug these numbers into the derivative. Now there's no factored form here. Because x is to the 2/3, we're always going to get a positive value from that. Remember, a rational exponent is power over root. And so if it's the second power, then it will always be positive. And so this is going to turn out to be positive, positive. So this is an example of a function that is increasing from -infinity to 0, and then again from 0 to infinity. Now what happens at x equals 0 that it's not increasing any longer? A couple of things could happen. We could have a sharp turn there, or we could have a, since the function is defined at 0, we either have a sharp turn or we have a vertical tangent there. One of those two things happening. And if it were a sharp turn, then we might get something like this. We would get an increasing and a decreasing, which we don't have. So I'm tending to think we have a vertical tangent at x equals 0. So let's take a look at that. And a vertical tangent would look like the second instance, where it's increasing and then it's infinite, so it's not really increasing, and then it goes back to increasing again. Or I should say it's not defined. Alright, so have we done everything here? There are no decreasing, never, and no mins or maxes here. So if we open up the graphing calculator, and let's see what we have here. We have x to the 1/3. Again, whenever you're putting a rational exponent into the calculator, you have to put it in parentheses. X to the 1/3 plus 1. And we're going to go ahead and graph. And you can see that, in fact, there is a vertical asymptote at x equals 0. Now we could have plugged that in and seen, let's move this over just a bit again. And I'm sorry, it's not a vertical asymptote, it's a vertical tangent at x equals 0. We plug that back into the original function. We'll see 0 to the 1/3 is 0, plus 1 is 1, so that confirms the graph. So we have a vertical tangent at 0, 1, and the function is increasing up to that point, increasing after that point, and never decreasing, and has no mins or maxes. So I'll take a picture of this and we'll go on to the next problems. And so that'll do it for this pair of problems here.